Welcome to part 5 of the crash course Cryptography. My name is Julian, and in this entire crash course that will probably go for around 25 episodes, we really want to cover everything from all the way to the basics down to the deepest holes of cryptography. And because I'm very much involved in blockchain and cryptocurrencies, obviously also kind of in relationship to different types of blockchains. And today we are talking about something that's not directly related to cryptocurrencies. We're talking about the only forms that are still kind of used of symmetric cryptography. And here we're talking about stream and block ciphers. And we're actually going to cover the most important cryptography that's used today in the entire world. And in cryptocurrencies, it's not really used. And this is the advanced encryption standard. The reason I still think it's relevant to cover and to cover right now is because you do understand some very basic ideas of cryptography. And you probably agree if you watched episode 2, and you should, if you're just watching 5, you should watch episode 2, because there we're giving an intro into all of that. And you will understand how it's much easier to understand symmetric cryptography compared to the asymmetric one. We're going to be covering asymmetric one after the episode from 7 onwards. 6 is going to be a mathematical introduction into asymmetric cryptography. And so, yeah, we want to kind of close this. But so there's going to be one important aspect that you're going to learn today. And this will be applied to something called hash functions, which we're going to be covering at one of the later episodes. And that's something that's very relevant, not only in cryptocurrencies, but in a lot of aspects in cryptography. So let's dive in and let's get an overview. I have my writing pad here. We are part 5. And let's talk about mostly advanced encryption standard. But let's build some basics to kind of understand that. Great. So let's start with the 2 major ones when it comes to symmetric cryptography. Remember, when we use symmetric cryptography, it is because we're using the same key for the encryption and we're using the same key for the decryption. So it's the same key, it's symmetric, and that's what this is all about. If you're not familiar with this, watch episode 2. Now, there's pretty much 2 types that have been used in this, and we're not talking about the archaic one like a Caesar cipher or just flipping a letter, which is basically a mod 26. We are really talking about the ones that have been used in the kind of last 50 years in the innovative kind of tech age. And basically what we have is we have so-called stream ciphers, and we have block ciphers. And we're going to be mostly talking about block ciphers, but just as a rough overview, let's start with the first one with stream ciphers. It was actually with GSM, very old kind of phone standard, that was the first consumer product that was using this kind of cryptography. And what a stream cipher does is, it's very, very straightforward. Whenever you have something that you want to encrypt, so you have a message, right? What you do is you put the message into bits. And this is really relevant because this is about the computer age, right? So we put it into bits. So we have these bits. And then, just like the name says, you have a stream as a key. And this is somehow encrypted. So this is the message M. And then you have a key. And the key is a stream. And every bit, and this is just an example here. So we have the stream here. We just make the stream because we're not going to talk about detail right now. We're going to cover it. And then what you're going to have is you're going to get your ciphertext. Right? And then the ciphertext on the receiver end, you again use the same key. And you're going to get M out of it. Right? Very, very simple message. And it's actually uber simple. Now, because we are using bits here, we are using, and this is relevant, mod 2 as a modulus function. And in mod 2, we have something very interesting. Because there's a couple of things that change a bit. And that is, the plus and the minus function are the same. And you can understand this in a very simple way. If we use, just as an example, 1 plus 1 equals 2, but in mod 2, this is 0, right? So if I would use 1 minus 1 equals 0, mod 2 is still 0. So this is a very interesting one, right? In mod 2, plus and minus is equal because of the mod 2. And this is very straightforward. There's another thing that's very interesting. And in software engineering or in computer science, we call this an XOR gate. And it does something that's really, really interesting. So let's draw something up and say this is the input bit. This is the key. And then this is the output. And the reason we're doing this is just because it really helps to understand certain things. Also, when we're going to be talking about hash functions, this is very relevant and very interesting to understand. So in inputs, we have 4 different types. We have basically different kind of options as inputs. So the input can be 0. So the reason I do 2 zeros is because the key can be a 0 or a 1, or a 0 and a 1. And now here's where it gets very interesting. So we have an output, which is an XOR gate, basically a mod 2 is the same thing. Now what you're going to be seeing is this. Whenever the inputs are the same, and that's the typical thing for an XOR gate, the output becomes a 0. And that's what the XOR gate does. If 2 inputs are the same, it becomes 0. If 2 outputs are different, so in this case, the outputs become a 1. And now we have some very, very interesting things. And this is very key to understand. Just because there was a 0 here, you cannot know if the input is a 0 or a 1. You don't know because it can be either. Also, you don't know if the key was a 0 or a 1. And the same applies with a 1. You don't know if the input was a 0 or 1 or the key was a 0 or 1. And this is really relevant because it really increases randomness in the entire thing. And this is very important to understand when we're talking about hash function as well. Because there is a very, very impossibility to kind of backwards calculate that, which is basically what you need. In order to get out of the output, you need the key. And so this is actually the key thing that we're not going to be going in, because this is the hard part. The hard part in a stream cipher is to generate this key stream. And we're not going to go into this because this is not relevant to us, how to generate such a key stream, for example, in telecommunication. Right? But this is where the hard part comes, how to generate that. And obviously, there's a lot of pseudo-random number generators involved in this because you need to have a key stream that's obviously predictable on both ends, but it still has to be random. But we're not going to be discussing this right now. I want you to understand how these stream ciphers work. Now, let's go into block ciphers. And block ciphers, we're going to go into, well, we're just going to discuss one, and that's the data encryption standard. That was kind of the first block cipher. But we're really mainly going to go into the advanced encryption standard, right? So let's kind of cover those. So let's talk about, so add always means talking about, right? Add to A, which is the data encryption standard. Also called AES. It's a very interesting one to know. Obviously, there's it's not used anymore. But basically, what it does, instead of encrypting every single bit, you encrypt, just like the name says, blocks. And in the case of the DES, you encrypt 64 bits worth of blocks. And this is what you're encrypting there. This entire thing has been proposed in 1974 by the IBM And it was a humongous thing. And obviously the NSA has helped there. And the DES cipher has become one of the best studied ciphers in the world. And this is very, very interesting here. And we're going to be discussing this a bit in more detail when we talk about the advanced encryption standards, but just so you kind of understand that. One idea that you can also do here is something called a Feistel cipher. And this is just a concept that you will hear again in when we talk about hash functions. And where here, the block that gets encrypted is symmetric. So this the symmetric, using a symmetric key. And this helps in the encryption and in the decryption. Now, the thing we're not going to be covering much in this, I just want to mention it for completeness, is in 1997, this thing was pretty much dead. So it had a good run, basically, for 23 years, which is long in cryptography. And it called for some new standard. And this is what we're talking about mainly now, to B, which is the advanced encryption standard, AES. And now this is really important. This standard is today, just so you kind of understand the importance of this entire thing. It's pretty much the most used encryption on the web. And this is really, I cannot kind of overstate how important the AES is. Just because it's not used in cryptocurrencies or in the major cryptocurrencies, it doesn't mean how relevant this thing is. It kind of came out of the DES being dead in 1998. There was a call for making submissions on what this standard could look like. And there were several submissions. And then in 1999, so a year later, they had these finalists. And the final algo was then chosen in 2000. And this is basically when this algorithm was chosen. And we're going to be discussing a couple of things today, how this kind of works. And so this is kind of where this all started. And this is something that's very relevant. Important to notice that even the NSA allows for the AES to be used for highly confidential stuff. So this stuff is really secure. And it's, it's very relevant. It works kind of like there's some basic building blocks compared to the DS. So instead of only encrypting 64-bit blocks, you encrypt 128, you can do 192, and you can even do 256 bit blocks. So the blocks get larger. The larger the blocks are, the more rounds you have to do. I'll talk to you about how these rounds kind of work. So here you need to do, I think it's 10 rounds. Here you need to do 12 rounds. And here you need to do the highest rounds, 14 rounds. Now, obviously, security goes up the more bits you encrypt and the more rounds you are doing. So basically what happens is you take the input, and instead of just like you do with a stream cipher, encrypt every single bit. With a stream, you have this block and you encrypt every block with a certain process. And these blocks have different types of sizes. 64 was in the DS. In the AES, it's 128, 192, 256. Now here, there's a couple of things in how you do it. So let's talk about how these rounds work. And again, we're keeping this quite a high level. And the reason we're still mentioning it is because it's relevant to understand this for hash functions. Hash functions use a lot of the same kind of tools. You do always these 4 steps in a row, except for the 4th step, you don't do it in the last round, and you will understand why. The first thing you're doing something called confusion. And confusion basically means you just substitute the bytes. 1 byte is 8 bits. And you're just substituting that depending on your key. Right? And you need to know the key. It's always the same thing. The key has to be known, right? This is a very important thing. Confusion, remember this word, it's going to be relevant. So this basically just means that they're going to get substituted based on the key. And this is the first kind of step in this algorithm. The second one is something called permutation. And permutation means that you do row shifts. And row shifts is very relevant. So that means that one byte, the way it gets encrypted, has an effect on the other bytes. And this is something that's very, very, very important because this leads to the third step, and that is something called diffusion. So basically, something moves out, and this actually means that you do a column mix. So all these blocks get split into bytes, and suddenly these things get completely messed around with, completely mixed, and this creates very, very, very strong diffusion. And so basically what these three things do here is you first of all confuse, so that means bits gets changed, but the way one bit gets exchanged, it affects all the other things, and it affects them in a very, 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 very unpredictable way. And this is essential, and the reason I bring this up so much is because, and this will be very relevant in hash functions, and we're going to be discussing this in detail there. When you have something called hello world, and you have an expression mark here, and then you do the same thing, but you have a period at the end, the way these things get encrypted or then hashed, it has to be completely indistinguishable. So it's not that one looks, let's say, and I'm just going to make stuff up here, AXBDX, and the other one looks as AXBDY. No. It has to look like this one looks AXBDX and the other one is B13YO. Just as an example, right? Obviously this is completely wrong, but I just want to give you the reason why. And the reason this is because of those steps: confusion, permutation, diffusion. This is very, very, very relevant. And then the last step is, and you only do this in all the rounds except for the last one, you do something called a key addition, where there's a subkey that gets generated from the main key and it gets added, and then you add a subkey, and then you start at number 1 again. Obviously for these number of rounds. So this happens 9 times with 128 bits, it happens 11 times with 192 bits, and it happens 13 times with 256 bits, the last step, right? And so this is the key thing. And this is how this entire thing gets circled. AES is uber secure. And we're going to discuss how to actually establish the key, because that's obviously the trick. How do you establish the key for this entire thing? But I want to give you a couple of ideas here, so that you understand the security here. And we discussed this actually when we talked about cryptanalysis and how secure certain things are in one of the last episodes, in episode 3 actually, when we talked about randomness. The 128-bit key. Sorry, not power 2, not squared bit. Has, like, to crack the key, right? It takes around 10 to the 18 years. So this is really, 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 really long time, right? Just as an example, let's do remember 10 to the 9 is billions, right? So the universe has been existing for approximately 13.8 times 10 to the 9 years. So it takes really, really, really long time. 192 bits is 10 to the 37, 256 bits is 10 to the 56 years, right? With current standards, obviously. Just as an example, the 64 bits that were used in the DES were in the minutes, right? So huge difference, obviously, right? So that's why we can't use this kind of standard anymore. Now, you kind of understand this, and obviously it begs one question, and that is, how do you define the key, right? How does the key get established? And this is where we kind of mentioned this a couple of times already. We're basically using asymmetric cryptography to create the key. And then we have the so-called session key that we're using for AES on the web. And this is the entire trick here. The reason we're doing this is because once you know the key, this is very simple to do. It's very easy to encrypt and decrypt. It's not computational intensive, but it's really, really, really straightforward. The reason we discussed this in this entire crash course, and here, there's a couple of things we are not discussing You can look this up yourself on the web. I'll make you some links. Also, if you're reading the book of Professor Parr, he talks about how to kind of establish this kind of stream. Another thing I'm not doing is I'm not going into the details of these rounds here because it's not relevant to understand the exact mechanism. No one of you is going to do this unless you really want to be a crypto designer. And for this, you need to take PhD level kind of stuff from the university, because this is really, really deep stuff. Because these things are very, very, very unpredictable in how to make sure that these things really encrypt with confusion, permutation, diffusion. This is something that's very, very, very key. So that one thing gets changed has an effect on its partners, but then also has an avalanche effect on the entire thing in an unforeseeable way. And this is the key thing to take away from symmetric algos, because you're going to need this for hash functions to understand how this is possible, that we can plug something in like hello world with an expression mark and then hello world with a period, but the output is completely indistinguishable and completely hard to understand. And how this works on the web is we have asymmetric crypto creating a session key and then using AES. I hope this is clear. Let me know if you have questions in the comments down below. If you like this stuff, let me know in the comments. Give me a thumbs up on the video. This is really highly appreciated. It motivates me to really push forward. I really like this. Subscribe to the channel if you want to hear stuff about crypto. Then obviously blockchain, a lot of entrepreneurship, mindset, and you're going to be notified all the time. See you at the next episode. Yours truly, Julian.